My name is Amit Biswas, and I'm going to talk about my research on web application on blockchain storage. Let's talk about the web.
Web is simply a collection of protocols that allows clients with browsers to talk to a web server, maybe running HTTP protocol. HTTP protocol is the primary protocol for the web. It's how we um, get files and upload files to web servers, and then that gets served to other clients on the web. So in order to establish a connection to a web server, we first start with Ethernet protocol, which can carry IP packets. IP packets can support TCP or UDP packets. TCP is for files that need to be sent in a correct order. This adds more latency. On the other hand, UDP is there is no reordering. You get the packet from the client or the server as fast as it comes. So if a packet comes out of order, you just simply drop it. So UDP is used for video chat applications, which require very low latency. And HTTP is mostly carried over TCP. HTTP provides a common way for browsers and servers to send each other files and talk in various other established manners. And what they transfer is websites or scripts that you can then see on your browser. It's basically transporting various files in different data formats that the browser knows how to show you.
Compared to the monolithic architecture of web as we know it, blockchain is a distributed architecture with a network of nodes where each node has a copy of other blockchain. And the blockchain contains all the transactions that have happened in that chain. Transactions make up blocks, and then blocks make up a chain. And blockchains are highly available and fault resistant because it's distributed, and we'll see later how this can be used to store data. This is an example of a Bitcoin blockchain. If you look at block 12, it has a previous hash field that links it back to block 11. There's a timestamp and nonce to prevent repudiation attacks, and there's the transactions that are in that block. Because each block links back to the previous block's hash, if the previous block is modified somehow, it would make the chain invalid. If an attacker wanted to maliciously modify the blockchain, it would have to modify it on the majority of the nodes that contain the blockchain, because everyone has the same copy of the chain.
So how does a client actually get a file from a web server on the web today? So we have a client with a browser that can support HTTP protocol, and we have a server out here called howstuffworks.com. In order for this client to establish a connection to this web server here, it first needs to know what the IP address translates to, what the domain name translates to in terms of an IP address. In order to do that, it has to talk to a DNS server that's also in the network, and then resolve the IP, and then finally establish a connection to that IP. Once it does that, it will ask for the file, and then the web server can decide that it has the file and it wants to serve it back to the client. That's the whole process. So in that process, any of these single point of failures can break and you would lose your access to your content.
What this means is you have multiple end users trying to get the same resource. That makes the bandwidth very limited from the server side. It also adds more latency because you have the DNS server, you have routers in between. It's not as resilient because if one of those devices on the network goes down, you lose your connection to the server. And it's centralized, it's highly centralized because all the data is contained in a very tiny portion of the network. And there's no guarantee that the data is permanent. If the data center dies, all the data goes with it. There's no guarantee that the data is safe forever.
Meet Interplanetary File System, or IPFS. IPFS uses content addressing versus HTTP, which uses IP addressing. What that basically means is it can be demonstrated with this picture of a cat that I uploaded to an HTTP server and then IPFS. On HTTP, it's uploaded to a single server and it has a web server running on port 1337. And if you want to request this cat image, you have to send a GET request for this cat.jpg. On IPFS, once I uploaded this cat, it actually got chunked into multiple blocks. And these blocks have unique hashes. What this basically means that the network, IPFS network, can perform deduplication and version control using those blocks. If there's an image of this cat that is very similar to another one, the content between those two images, that is the blocks in those images, if they're the same, it would only be stored once on the network, which saves a lot of data and performs deduplication. And version control works in a similar fashion like Git using Merkle-DAG. I'm not going to get into that right now, but the idea is that it can store different versions of the same file as in a directed acyclic graph on the transaction chain in a block. And just like we discussed before, because it's a blockchain, each node stores some content and index information. If the file or block size is small enough, it can actually store the data directly in the blockchain. If it's big, if the block is bigger, then it will simply have a link in the blockchain telling the client which node on the network has the data that you're looking for.
Because IPFS is a distributed protocol, it has improved routing and latency to the content that you're looking for. If you are here, for example, and you want the picture of a cat, if you had requested that picture of a cat before, chances are the nodes nearby, near you, have already cached it, which means you can simply, once you request it, the distance between you and the node that has the content is going to be very small, is going to be local. On HTTP, the content doesn't get cached in a local, within the local network per se. There's no edge network that caches the data. You have to, every single time you want the data, you have to go to that web server, even if it's hosted on Antarctica, which adds a lot of latency. As I mentioned before, the IPFS DHT, distributed hash table, can store values less than a kilobyte directly on the blockchain. Otherwise, you'll simply store a link that can point to nodes that has a copy of that data. And the data is exchanged between the nodes using a protocol called BitSwap, which is very similar to BitTorrent, which basically means that if you're, say you're trying to download that cat image, you simply ask the network, who has my cat, and anyone that is storing your picture of a cat will respond back to you
and then you'll have a list of nodes that you can acquire the data from in parallel. And Merkle tags are used to structure the data in the blockchain, and it also provides version control for that data. Because of all those features of IPFS, it's actually a great candidate to replace the internet, replace HTTP. In order to test whether IPFS is a good candidate for serving files or hosting applications on the web, I uploaded a picture of this cat on a virtual private server running an HTTP server. And then I also did the same, but with the virtual private server running, the same virtual private server running an IPFS gateway. IPFS gateways are the middleman between my browser's HTTP request. It basically takes the request and then talks to the IPFS network and then gets the file from the network and then serves it back through HTTP. Because browsers don't support HTTP or IPFS protocol natively, we need gateways in the interim. I also ran an IPFS gateway directly on my client. This is the intended way for joining an IPFS node and getting files from the IPFS node. And I also used IPFS.io IPFS gateway to see if those are any different. I also used a private IPFS gateway, or IPFS gateway hosted by a private company. In order to test the latency, I used a program called Apache Bench, and I configured it to request the image of a cat 1,000 times. And I basically measured how long it took for each of those requests to complete. For the purposes of demonstration, I only used 2 results here. My research paper has the data for all the other requests in the previous slide, all the other tests in the previous slide. As you can see, the bulk of the request for HTTP completed on the 14-second mark, and then it took, I think the last request completed around 19-second mark. As you can see, the average processing time, total processing time for HTTP was 55 milliseconds, with a lot of variance. The maximum time it took for finishing or serving a request was 3,040 milliseconds. The request probably up here. And you can see HTTP got overwhelmed as the number of requests piled on. This is kind of expected because the VPS is virtual private server is hosted in Canada, so it's a long distance, and the virtual private server doesn't have enough processing power to process 1,000 requests at a time. Compare that to my IPFS gateway that's running on my client, on my machine. It took less than a second to complete all 1,000 requests. That's why the line is completely straight. You can see the average time it took to complete 1,000 requests is 2 milliseconds. And the connect time is 1 millisecond because the IPFS gateway that my browser connected to was directly on my local machine. As we saw, because of IPFS's distributed nature, retrieving files repeatedly is insanely fast. To incentivize storage providers to store your data, it has its own native currency called Filecoin. It is not released yet, still under development.
you can provide, you can basically pay in Filecoins to make sure data is um, redundant on the network and it stays permanent on the network. And most data on the IPFS network will be permanent. As long as people are requesting data, it'll be stored on enough nodes, it'll be cached on enough nodes that it will never be deleted. But there's a possibility that if you didn't pay for the data and you just want some data to be stored, but it has never been requested by anyone, there's a chance that it might get deleted. And IPFS is much more decentralized. As you saw, if a node dies in the network, you still have all the other nodes that can serve your request. Compared to Bitcoin, Bitcoin is just proof of work, which means if you control more than 50% of the computing resource, you can modify the blockchain if you wanted to. IPFS is not exactly using proof of work, so it is more resilient to manipulation simply by brute force. There's a comparable file system called Swarm that is using Ethereum as the native currency. I believe both will be trying to do the same type of trying to serve the same type of service. I think both intend to replace internet, but as of now, Filecoin or IPFS looks to be the way to the future of file storage and the internet. Thank you.